Hallo Wolfram.
Stefan, can you hear me?
Yeah. Are you recording on purpose?
Stefan, I didn't hear you reply.
Yes, I hear you.
Okay, good. And the picture is there as well, I hope. Okay.
Yeah, but
Okay.
are you recording on purpose?
Yes.
Okay.
So the idea is then that this recording will be uploaded.
I see.
So last time there was a problem with the stream, apparently. Although I've been told it should appear eventually. Okay. Okay, good afternoon, everybody. So today we continue with the electronics lecture. Maybe before we start, there's this doodle poll for people who want to do the assembly of the project PCBs. So far, I think 16 people have signed up. I would have expected a little more. So we'll leave it running for a few more days, and then we'll send you a message afterwards to tell you which of the time slots you've been allocated to. Okay, so let's start. Last week, it was mostly about the transistor circuits, the small signal transistor model, and we used this model to analyze in more detail the emitter follower, or also called common collector amplifier. We also looked at the common emitter amplifier, which is an amplifier that has significant voltage gain. We saw the so-called Miller effect, which is problematic for high-speed circuits, where the input is coupled capacitively to the output with a large swing, making this capacitance look much larger than it actually is. Then we discussed these transistor capacitance a bit and concluded with the high frequency model of a transistor, where the transition frequency appears where the gain of such a transistor drops to zero because of capacitive effects. We'll, at the end of this session, see a similar quantity for more complex amplifiers. So the plan for today is to start looking at some amplifier building blocks. So we'll work towards a realistic amplifier. One element we look at is the cascode, so-called cascode. Another one are current mirrors. And then finally, we move to differential amplifiers, which are very widely used. We discuss the principle of operation, analyze it a little bit in the small signal picture, and then move on to different types of differential amplifiers with high gain, and finally towards the so-called operational amplifier, and briefly discuss negative feedback and stability. Okay, so let's start with a reminder. So this is the common emitter amplifier, where you see the Miller effect due to the capacitance between the base and the collector, which is then amplified because this has a voltage gain. So the okay, here's the first mistake. So the gain is of course the output divided by the input, which is, so the output swing is much larger than the input. It's actually in the opposite direction. For this one, it's an inverting amplifier, so that the effective capacitance is multiplied by a factor a plus 1. That is the so-called Miller capacity. Another effect that we have here is that the output swing, this is the output node, which is connected to the collector of the transmitter, changes the collector emitter voltage of this transistor. And through the early effect, this also changes a little bit the output current here. So it's not an ideal current source, but there's also a small early effect. And today we'll see a circuit that avoids both of these effects, and that's the so-called cascode. So so you see now the same kind of amplifier that we just looked at. So this is the modulating transistor, this is the collector load, but now we added a transistor between the collector of the input transistor and the load, which has its base fixed to a constant potential. So now the amplifying action is such that this transistor defines the current that flows down this branch here, so through the transistor and hence also through the load, while the cascode transistor now fixes this potential with respect to the cascode voltage. So here we have this the base emitter voltage, and the current that flows is a steep function of this base emitter voltage, and hence this point moves very little. So in the large signal picture, this is shown here. You see here the on the horizontal axis the potential of this node, and in the vertical axis the current that flows down this branch. So from the point of view of the input transistor, this is the red curve, so the well-known transistor curve. It starts quickly, then it goes into saturation and is almost constant with a small slope due to the collector, the small slope due to the early effect. Now, on the other hand, if we look at the current through this transistor here, it is controlled by the voltage difference between the cascode and this collector point. So that's the voltage basically from here downwards. And here you have this very steep diode IV curve that you know very well. And of course, the currents have to be the same. So they meet at some point here. And if we change the current that is flowing through this transistor, you get the usual effect that this changes only very little where this intersection is on the horizontal axis. So this point is almost fixed by the cascode transistor. In the small signal picture, we would say that this transistor has a very small emitter resistance, which is like 1 over Gm, which is of the order of a few ohms. While this transistor here has a huge collector resistance, which is given by the early effect, and is typically of the order of 100 kilo ohms. So here we have this voltage divider, or you can, if you want, you can look at it as two springs. This is a very stiff spring, and here you have a very loose spring. So it's basically wherever you move this point that this one has to follow, while the lower transistor has very little impact on the potential here. So this means that the cascode transistor shields the input transistor from what the load does. So clearly, when we change the voltage here, the current here changes a lot, which makes this point move up and down. But you see very little effect on this node here. So for this transistor, it's a little bit like the load was not there at all. So that means that this transistor is fast, even when we have a signal source with a significant impedance, because it only sees the linear capacitance, so the normal capacitance to the collector and to the emitter, but it does not see the early effect because this mode doesn't move very much. So the question is whether we now have simply moved all the problems to the other transistor, and the answer is no. Because this transistor now has a fixed potential at the base. So the cascode voltage is a fixed voltage, so there cannot be a Miller effect. Then the cascode emitter is the cascode, yes, the emitter current is fixed by Q1. So the current that flows down here is given by this transistor because it doesn't have an early effect anymore. And the collector current is basically the same. There's only a small difference between the base and the collector current, which is the base current, which is very, very small. So somehow there cannot really be an early effect in this transistor because of current conservation. So the current that flows in has to be the same as the current that flows out. Now you may wonder how is it possible that this transistor has no early effect? After all, it is still a transistor with a finite early voltage, and the collector moves up and down a lot. So why is there no change in the current here? And to do that, we first look at the situation when we have the cascode transistor not with the input transistor attached to it, but with a constant potential. And in that case, we would in fact see a large early effect. So now, when we have a variation of the voltage here, we will see a variation of the current that flows because of the early effect in the cascode transistor. But the situation now is slightly different. The bottom transistor, the input transistor, behaves more like a current source. So this is a high impedance point, which means that this transistor can compensate large current changes with small potential changes at this point. It doesn't need to change the collector voltage. So it basically compensates the voltage swings here by tiny voltage swings here. So these are still so small that they don't have an effect on the input transistor, but they completely eliminate the early effect here. Okay, so the bottom line is that the cascode now translates all the variations that comes from the load that we attached here to tiny changes here at the of the emitter potential. So that means that the cascode really removes the Miller effect completely, and it does not compromise the gain. So we still see the full gain of this amplifier. let's see this in a simulation. So this is now an emitter amplifier without the cascode that we've seen before. It has uh, a small emitter uh, degradation resistor here, but which defines the gain. So we have the gain that is given by the ratio of these two resistors. And let's say we have an input resistance of 1 kilo ohm, which is usually part of the signal source. Now, what you see here is this RC time, the slow behavior at the base, and as a consequence of that, also at the output due to the Miller effect. So this resistance sees the capacitance, the Miller capacitance here. Now we added the cascode to the same circuit, and now you go from the red circuit, from the red signal to the blue one. So the Miller effect basically completely disappears. The base is fast now because there is no Miller effect, and so the output is fast as well. And as you can also see, the voltage here, the cascode node, which is shown in green here, makes a very, very tiny step only. So there's almost nothing happens here. All the action is at the output. The gain is essentially the same that we've seen before, um, but the amplifier is significantly faster than it was without the cascode. So the only disadvantage of this is that the circuit needs a little more headroom. So you cannot go as far down with the output as you could without the cascode, because you need to keep both transistors in the active region. So the output can never go well below the cascode potential here. So we can also analyze this more qualitatively using the small signal picture. If we need more than the qualitative results, so we can do the small signal analysis. So here we have the equivalent of this circuit. So these are the two transistors with the hybrid pi model and the load resistor on top of that. So as an example, we look at the so-called output resistance. So the output resistance tells us how much the output voltage changes when the current at the output changes a little bit. And this is only a property of the cascode. So we look at the current here and the output voltage. So we don't need to include the resistor itself in our circuit. So we leave that out. Then the uh, cascode voltage is constant and the input voltage is constant. So we really want to see what happens here when we play at the output. So we connect these two resistors to constant potentials. And as you may remember in the small signal analysis, a constant voltage can be set to 0. So this resistor is between two equal potentials. We can drop it completely. And since the input voltage is constant, this is also a constant current. So in the small signal current, we can drop it completely. So this is all we're left with. So we have these three resistors and one current source that is controlled by the base voltage, by the yeah, it's by the difference between the base and the emitter of this transistor. Okay, so to analyze this circuit now, we start with the current balance in the output node, which is here. So we have the external current we call I out flowing in from here. Then we have the current that flows through this resistor, and this is given by the difference between V out and VC divided by RCE2. And we have this current here, which is given by the transistor action. So it's the GM multiplied by the base emitter voltage, and the base emitter voltage is V is the cascode voltage minus VC, and the cascode voltage is 0, so we have only minus GM VC here. Okay, so it's minus GM2 times VC. So we separate the terms with the V out and the VC, and then this reads V out over RCE minus, and then this is 1 over RCE2 plus GM2 multiplied by VC, which appears here and there. So we still need a second equation because we need to eliminate this VC. The second equation comes from the second node where you can look at the current balance. So the same current that flows in here must also flow out there. So again, we have I out is VC divided by RCE1 is the current flowing through this resistor, plus the current flowing through this resistor is VC divided by RBE2. So so this we can change around, and then we say VC is I out divided by 1 over RCE1 plus 1 over RBE2. And this is, of course, the same as the parallel of RCE1 and RBE2 multiplied by I out. Okay, so now we can use this and plug it into this equation here. So now we can eliminate VC, and then we're left with something that contains only I out and V out. So I out is V out over RC2 minus this factor here multiplied by this term. So now we need to sort the terms, and then we have our relation between I out and V out. This is done here. So we have all the terms containing V out on the left-hand side and all the terms containing I out on the right-hand side, and this will give us the ratio of V out over I out. Which is here, so copied from the last page. In order to make a bit more sense of this, we make some approximations. So GM times RC is typically a number that is much smaller than 1, much larger than 1. So remember, this is the early effect, which is typically a resistor of the order of 100 kilo ohms, while GM is the inverse of an ohm typically. So this is a number which you can also see for the bipolar transistor. GM is the collector voltage divided by the the collector current divided by the thermal voltage, while the RC is the early voltage divided by the collector current. This cancels. So what we're left with is the ratio of the early voltage over the thermal temperature. So this is typically for a bipolar transistor 100 volts over 25 millivolts. So this is a very large number. So we can neglect the 1 here, and we're left with only that term. So we have v out over V in is RCE2 plus GM times RCE times RCE2 times RBE, where we have neglected the RCE1 also with respect to the RBE. And now this again here, GM times RBE is the beta of the transistor. So what we're left with is RCE plus beta times RCE. Okay, so again, this is a huge number. So we multiply the early effect of this one by beta. So we have a huge increase of the output resistance by the cascode action. Remember that an ideal current source has an infinite output resistance, so infinite differential output resistance. So making this a large number is a good thing. This is the same. Oh yeah. So the fact that we can neglect the output resistance here means that our gain is simply given by the GM of the input transistor multiplied by the load resistor that we attach here. And then the negative sign comes, of course, from the fact that this one goes down when we go up here. Okay, another thing one may want to study is the cascode voltage sensitivity. So the question is, do we have any disadvantage from the fact that we added this transistor here? So what happens if there is something happening on this cascode voltage? There's a little bit of a vibration here, some perturbation there. Are they amplified and show up as huge signals on the output? So this we can also do in a small signal analysis. So the bottom line is that the result will be they are not. We can use the same picture here, but the simplifications are slightly different because now we have to keep this resistor here. Without that resistor, it's not really defined. Okay. We can still drop the RBE1 because we keep the input constant, the input voltage constant. and we can drop the current source. Um, so again, we do the same thing with the output node current balance. So uh, the current here is now not just I out, but we say I out is V out divided by R with a minus sign. And then the other two are the same. So I have V out minus VC divided by RCE2 is the current through this resistor. And then here the current is GM times V cascode minus VC. This time, last time, you may remember that we had V cascode 0, so there was only minus VC GM2. Now we have to keep V cascode because we want to see how V out changes as a function of the cascode voltage. Okay, so again, we can rewrite this a little bit. So we have we want to sort the terms that contain V out and VC, and this is just rearranging this. And to make things a little bit easier, we immediately drop the RCE2 compared to the GM. So this is a very small contribution. So we're left with only V out over R, which is this term, plus V out over RCE2. We've taken an overall minus sign here. And this is GM2 times VC minus GM2 times the cascode voltage. So the first thing we see here is that the cascode voltage is, the collector voltage here is given by the cascode voltage plus this correction, which depends on V out. And since GM is a large number, this is a very small correction. So this is what we've already said before. Now we confirmed that in the small signal picture, that this node here basically follows the cascode with only a very, very, very tiny correction. To move towards our goal to find the output voltage, we must again eliminate this. So we again look at the current balance here. And now we have again the current flowing down, which is V out over R coming from here. And we now also have the current that flows through this resistor, which is the cascode minus VC divided by RBE2. And the current flowing down through this resistor is giving the VC over RCE1, similar to the previous case. Again, rearrange terms slightly, bring the two VC terms on the other side. So now we have here V cascode over RBE2 minus V out over R, and we have this, which is again like the parallel of RCE1 and RBE2 multiplied by VC. And here we can now plug in the VC that we have here. And this way we eliminated VC. This now again contains only V cascode and V out. And then we have an equation that contains only the voltages that we're looking for, which is repeated here now. Again, you sort the terms and you find this relation that the V cascode over RCE1 is a sum of 1 over R, which is this term, plus 1 over R star, which I just defined here for shorthand, multiplied by V out. So now the output of the cascode is given by this ratio here. And in order to make sense of that, we approximate again by saying that RCE1 is much larger than RBE2. And then our R star can be simplified a little bit. And so this one, we drop the RCE1 here. And here we drop the RCE1, and then we're left with only this product, RBE2 times GM2 times R parallel RCE2. Again, we have GM2 times RCE2 is better. Sorry, GM2 times RBE2 is better. And this term remains. But the end result is typically something that is much, much larger than R, because RCE2 is typically larger than R. So multiply this by the beta of the transistor, which is of the order of 100 or so. We get something that is much larger than R, and we can, to a good approximation, say that this is simply minus R over RCE1. So the whole thing is quite messy, even in this small signal approximation. But when we make some reasonable approximations here, we can get a result that can be understood. So what this means is that the cascode emitter, uh, the emitter of the cascode, which is the collector of the input transistor, simply follows the cascode voltage, and this modulates the current in the input transistor over the early effect. So we have this dependence, this proportionality to 1 over RCE1, which comes from this early effect. And then we convert this to an output swing with the output resistor here. So it's understandable that the whole thing is proportional to R over RCE1. And since for most realistic configurations, this R is much less than the output resistance of this transistor, we come to the point that the output voltage is affected only very little by the cascode voltage. Okay, so this is a good thing, because it means that we don't need to fear that any perturbations on the cascode are multiplied, or any noise that comes from here destroys the properties of our amplifier. Okay, so far so much for the cascode. Now we move on to current mirrors. And part of the current mirror is the so-called diode connector transistor. This is shown here, where we take a transistor and tie the base and the collector together. So this means that the base collector diode is always in zero bias, which means that the transistor is always in active mode. So it'll always work nicely. It does not mean that you can basically ignore this diode. And you only have this diode. It's still there. It's still a transistor. So the base emitter diode current, which you of course now have here, is still boosted by the amplification of the transistor. But the net effect, of course, looks just like the diode. So it's what you see is a multiple of the current that flows through the base emitter diode, multiplied by beta plus 1 when you look at the collector. So this is the usual exponential curve here. Now you may wonder, why would I want to do this? I can then also, of course, take a diode, which is true. This becomes interesting when you combine it with a second transistor, which is the same. Now this is done here. So here we have the diode connector transistor, and we have next to it an identical transistor, which has the same base potential. So we connect the bases here. And so the left one here with the diode connection has this IV curve here as the function of the collector emitter voltage, which is also now the base, of course, the base voltage of this transistor. So as a function of this voltage, we see this curve on this side, and on the other side, right. And on the other hand, we see this collector emitter voltage here, and we expect these curves, and which are relatively flat. So you'll always end up in this region here. Now, if you look at the second transistor, both transistors have the same base emitter voltage, so they're on the same red curve. But the collector emitter voltages are slightly different. But because the fact that they have the same VBE means that they give you roughly the same current, with the exception of the early voltage. So if the collector emitter voltage of the other one is very different, you get a slightly different current here, but it's only due to the early effect. In principle, they both have the same base emitter voltage, so the current is the same except for the early effect. So the base current that flows down here is a small contribution. If you neglect it, then you come to the conclusion that this current is always the same as that current. So what we've done here is we took a current 1 and produced a copy of it at the output of this current. And this is indeed the ingredient of many amplifier circuits. There are some variations of this. There are actually many variations of this. One of them is if you take different transistors, where the one on the right-hand side has a different beta, for instance, a larger beta, then you get a scaled copy of your current. So if this one has beta 2 and this one has a beta 1, then the current here will be uh, multiplied by beta 2 over beta 1. This is, however, not used very often because the beta, as we've said before, is not well controlled. So if you want a precision circuit, you typically try to make these transistors as similar as possible, and one can often see them matched with layout techniques, or you can buy them in a single package. So two transistors that are already connected in this way and are built in a way that they're as similar as possible to get the matching done as well as possible. Another thing is that one often tries to make multiple copies of the same current. So you program a current here and you make multiple copies of these that you need in different places of your circuit. So this type of distribution of a current is very often found in integrated circuits. Of course, you cannot do that too often because when you have hundreds of these copies, then the base current will start to play a role compared to the collector current here. An example of what one can do with a current mirror, this time now with a PNP transistor. We've seen previously the pictures with an NPN, but you can do the same thing with a PNP. So let's say you have a circuit block that should run with a fixed current. You don't know a priori what kind of voltage you will find across this circuit for the current that you give it. It may even change over time because of temperature or whatever effect. But you want to keep it at a constant current. And a simple way to do this is to use this current mirror. So on this side, now you take a resistor that is connected to this diode connected transistor here. So this point will be always roughly 0.7 volts below the supply voltage. So the current here will be fixed and given by the resistor. So it's this 4.3 volts divided by 1 kilo ohm, for instance. And then this guy here will always send down these 4.3 milliamps, no matter what this circuit does. So you have a nice current source here, which you can program with this resistor. And if it's a good current source, then this current will, of course, be independent of what the actual voltage drop across your circuit will be. We've seen that the current on the other side is a good copy of the input side, but it's not a perfect copy because of the early effect. If you need to eliminate the early effect, there's actually a nice trick. So one could do something like a cascode here, of course, but that would need then an additional voltage. And Mr. Wilson found a nice trick to do without any additional connection, just one more transistor added here. This looks a little strange now because we are trying to mirror the current from here to here, and still the diode clamped resistor is now on that side. But I will try to convince you that this actually works. So now we have the external current source here, and this point is kept at some potential. Don't know what it is at the moment. It just needs to be high enough to keep these two transistors in the active region. And then again, like in the ordinary current mirror, the base emitter voltages of these two transistors are the same. So the currents will, of course, be very similar. But this is now also the collector emitter voltage of this one. And so all these voltages are of the order of a diode voltage, these 0.7 volts. Now, if you look at this point here, which is the base of the third transistor, we know that this cannot be very far from this node. So this one will also be roughly one diode above this potential here. That means that the total collector emitter voltage of this one will be roughly 2 diode drops. Okay, and therefore the collector emitter voltage of this one is 2 diode drops. The collector emitter voltage of this one is 1 diode drop. So they're always very close. There's only a small difference in the so there cannot be a large early effect. So this means that the current that flows through these two transistors is basically identical with only a very, very tiny correction. And now this current here now must, of course, also flow to Q3. Uh, and the early effect here is eliminated in a way that is similar to what happened with the cascode. So we don't see the early effect of this one, and we have no early effect here because the collector emitter voltages of these two are almost the same. So if we again neglect all the base currents, we have a perfect current mirror that is completely independent of the load potential. This is shown here. You see a comparison. In red is the standard two transistor mirror, which starts mirroring very quickly because the transistor is always active. But you see how the early effect starts to a small imperfection of the behavior. So if you pull up the point on the right hand side, you start seeing slightly more current. On the other hand, with the Wilson mirror, you need a certain voltage to make both transistors here active. So it starts only operating at something like 0.8 volts here, but then it's absolutely perfect. There's no deviation from the constant current behavior here. Um, so let's also look at a possible amplifier with the current mirror. Again, we start with the common emitter amplifier that we've seen before, which is shown here, and the gain is given by the ratio of the collector resistance and the emitter degeneration resistor. Now we again start with the same thing. We have this transistor here, which is a bit like an emitter follower, moving this point up and down, setting the current through this resistor and this current, and then here it flows through the load and creates the voltage drop that gives us the gain. But now instead we attach the current mirror, and now the same current is flowing down here, and we can put the collector load instead on this side. And now the gain is positive, which is not a great advantage. It's just what it is. But it has several advantages. So one advantage is that for this transistor, the output potential is almost completely independent of the of your supply voltage. If you change the supply voltage, it does not change the current here, only through the early voltage of this transistor. But the main effect is that the current is set by this transistor and the resistor. And this current is mirrored here, also independent of the supply voltage. So what your output does not change with your supply voltage, which is good. The other big advantage is that this node now has a lot more headroom for output swings. So it can basically go from 0 to almost all the way up here when you start shutting down this this current source. But it can go almost up all the way up to the supply voltage. So you have almost a maximum possible output swing, and this is a good thing, especially when you make circuits with low operating voltages. While here, this output can never go below the input voltage, because then you start killing this resistor. Okay, here you're completely independent. You decoupled your input from the output, which also means that you have no Miller effect, because this node is basically fixed by this diode clamp here. So there's no Miller effect from the input to a node that moves fast up and down. Only this node moves fast up and down with a large swing. This one is almost constant, so there's no Miller effect here. So these are two things that there are nice improvements for an amplifier. Okay, now we move on to a different kind of amplifier. So the ones we looked at before, they take an input voltage and translate it to an output voltage with some gain. Now we switch to difference amplifiers or differential amplifiers. So they don't amplify a single voltage, but they ideally amplify the difference of two voltages. So the idea is that for such an amplifier, if it's ideal, the output voltage is a multiple of the difference between the two inputs. Of course, this can only work when this is kind of in a symmetric situation, and in a realistic situation, there will be an offset to this. So when you have an operator and a transistor, an amplifier that operates between 0 and some positive supply voltage, then this offset will be typically maybe of the range that you have, but still the deviations from this will be proportional to the difference of the input. So when you have an ideal uh, difference amplifier or differential amplifier, then the output should be independent of the common mode. So it should not matter where these two are. It should really only depend on the difference. And this is called common mode rejection, which is, of course, only true for an ideal transistor, for an ideal amplifier. So why do we use difference amplifiers or differential amplifiers? One of the reasons is that differences between two potentials are much less sensitive to interference or crosstalk or pickup. The whole thing is also a lot less um, uh, prone to suffer from supply voltage variations, but and also other effects often cancel. When you have two voltages that suffer the same effect, the difference is always much more stable. So looking at the difference of two voltages is a very good tool for making your circuit better. These transistors, a certain class of these transistors where this gain is very large, is called operational amplifiers, and these are extremely versatile and can be used for a lot of things. And there will be a whole lecture, I think, about it by Georg in 2 weeks. But before we come to how these things are used, we will today discuss a bit how they work. And I think before we start this, we take the break now and then start looking at the principle of operation of the differential amplifier after the break in 15 minutes. Okay, so welcome back. Um, for the rest of this lecture, we'll try to look at circuits that do this. What is shown here? So they take two voltages and produce an output that is proportional to the difference of the two. And one very common configuration is shown here. Can call it a differential pair of transistors. Um, so you have two input transistors and NPN transistors in this case, um, both connected to the same, so the emitter is connected to the same potential, which we call VE here, and both have a collector load uh, connected to the positive supply. And the output will be these collector nodes. Um, so the base emitter voltage of these transistors, Q1 and Q2, depends, of course, on VE, but also on V1 and V2. Let's first consider the situation where V1 and V2 are the same. Um, so then this means that the currents through both transistors will be the same. And at the bottom here, connecting from VE to ground or the negative supply, we have an ideal current source. Um, so the sum of the two currents will be I0. And if everything is perfectly symmetric, then of course each one of these currents is the same. So we have the same current flowing through these two transistors, which means that we have the same current flowing to these resistors. So that means that the output and inverted output will be the same. And we call this will be the offset voltage V0. Now, if we go away from the situation where V1 and V2 are the same, let's say we make V1 slightly positive with respect to V2. So now we have a higher VBE here than we have there. They still have the same emitter potential, but the base emitter voltage of this one is now higher than the base emitter potential of the second transistor. And therefore, the current that flows here will be higher than the current that flows there. Now the sum of the two currents is still the same. Therefore, we will have a current that is larger than half of the current on this branch and a current that is smaller than half of the I0 on this branch, which means that with respect to this offset, here we have a higher current, so the so-called inverted output will go down because there's more current flowing, and the non-inverted output will go up because we have less current flowing through this one. So we have this hierarchy here. So the output, this output is higher than the offset voltage, and which is again higher than the inverted output. Now, if you go in the other direction, so now we make the left potential more negative than, and the right one goes higher, then we have more current flowing through this side, which means that this resistor will this resistor sees more current and the voltage drop is larger, so this point goes down and this one goes up because there's less current flowing here. A bit more qualitatively now, again using the small signal analysis, these two transistors modulate the current that flows, I1 and I2, and for this we neglect now the difference between the collector current and the emitter current. They're almost the same if you neglect the base currents. So now the current in the left branch is given by the GM of the left input transistor multiplied by the base emitter voltage, and the base emitter voltage is the difference between this voltage and this common emitter voltage here. And on the other hand, we have the same thing for the second transistor, assuming they both have the same GM. Now, if our current source is indeed an ideal current source, then the current will be the same, which means that in the small signal current will add up to 0. So there's no change in this. So the differences from the working point will add up to 0. So I can plug in what I have here. So this is GM times V1 minus VE and plus GM times V2 minus VE. In this case, GM drops out, and we just have V1 plus V2 minus 2VE is 0. And this means that VE is basically the arithmetic mean of these two voltages. So it's always between these two, regardless of what they do. So when they both go up in the same way, it'll just follow. And when one goes up and one goes down by the same way, then it doesn't change. So it's always in the middle between these two. If we have a purely differential drive, so that V1 is minus V2, then it'll stay constant. But in general, we cannot expect that, so we may have a bit of offset, and so one goes up more than the other one goes down. And we can still write down what happens. So the output voltage, which is this one. This one is the inverted output. Let's look at the non-inverted output. Is given by minus R times the current in the left-hand branch, in the right-hand branch. So it's R times I2, which is R times GM times V2 minus VE, because this module is the transistor modulation. Now for VE, we use that it's the V1 plus V2 over 2. And then we get that this is V1 minus V2 over 2 minus V1. So minus V1 over 2 minus V2 over V2. Yes, so we end up with this expression. And so the output is proportional to the difference of V1 minus V2, which is just what we wanted for a differential amplifier. And this will be the gain. So GM times R over 2 is the voltage gain of a differential amplifier. And this is in this sense also a perfect amplifier, because it depends only on the difference. So there's no term here that contains the sum of the two. So we have perfect common mode rejection for this arrangement, but this is true only in case that this is actually a perfect current source. Let's see at what we can get here for a bipolar transistor. GM, as you know, is the collector current divided by the thermal voltage, 25 millivolts. So and the collector current of each one at the working point is 1/2 the current of the current source. So you can write that the differential gain, so this expression here is roughly like R divided by 100 ohm times I0 divided by 1 milliamp. So if you had an amplifier now which has 100 ohm collector load resistors and 1 milliamp of current, you would have a gain of 1, but you can easily, of course, turn this into a kilo ohm and then go to 10 milliamps, then you already have a voltage gain of 100. So this is a good way to produce significant voltage gain. Now we drop the assumption that our current source is perfect. So no current source in real life is, of course, perfect. They all have some finite resistance, which is modeled here by this parallel resistance resistor RK, which is a differential resistance again. So now VE is given by RK times the current that the sum of the currents through these two nodes, right? So this current source is constant, so the differential currents, the deviation, has to flow through this resistor, and gives rise to a voltage drop RK times I1 plus R2. So now again, we plug in the expressions for the currents. So here we have GM times V1 minus VE, and here we have GM times V2 minus VE, which is the transistor modulation. And now sort the terms. So here we have RK times GM times V1 plus V2, appears in both. And we have a minus 2 RK GM times VE, because this also appears in both. So now we have VE on the left and the right hand side. So bring this over to this side and divide by 1 plus 2 GM RK. Then we get the result, and then we plug in a factor 2 here and divide the sum by 2 here, we end up with this expression. This is now the common mode. So this is uh, the average of the two voltages, and this is a factor that it's multiplied with to give us this VE. And since GM times RK is typically a very large number, so GM is large, is the gain of the amplifier, and RK for a reasonable current source is not infinite but should still be large. So this is a number much larger than 1. So we can approximate this expression here as 1 minus 1 over this term. Okay, so it's almost 1, but it's not exactly 1. Okay, so the emitter still follows the common mode of the two voltages, but the factor with which it follows is not exactly 1. And the reason that it's not exactly 1 is, of course, that this RK always pulls it down a little bit. So the factor is slightly, the factor in front of the common mode is slightly less than 1. Now, this may seem insignificant. However, it leads now to a common mode amplification of the whole thing. So let's see what the output does. It's given by the collector load resistor R multiplied by I2 as before. So this is then again GM times V2 minus VE. But now VE is given by this expression that we derived on the previous page. Okay, so now we have V out depending on this term, which now has V1 and V2 as before, but in a slightly different way. So we have one term that is proportional to V2 minus V1, which we get when we add up this V2 and we take the factor 1 here. This is of course what we had before when RK was infinite. We had only this term. But now we're still left with the other term. So we have this 1 over 2 GM RK multiplied by V1 plus V2 over 2. And this is left here. So instead of only this ideal term, we now have also something that is proportional to the common mode. And this is now rewritten here in this way. So we pull this one into the in front of the two terms. And these factors now have names. So this one is the differential gain, as we had before, R times GM over 2. And this one can be called as a common mode gain. So this is how the common mode of the two voltages is amplified. And so this is called a differential, and this is sometimes called a common mode. Of course, this one is much smaller than this one. This has GM in it, and this one has 1 over RK, which should be a small number ideally. But it's not 0 because current sources are not completely perfect. So here we again have these two amplifications, the differential and the common mode amplification. And a quantity that is then often formed is the ratio of the two. So the ratio of the differential gain divided by the common mode gain. And for this circuit, this is then GM times RK. This is called common mode rejection ratio, or CMRR. And it's an important quality indicator for a differential amplifier. So if you buy a differential amplifier somewhere, then you will usually find this number given somewhere. Here in this ideal case, it's given entirely by the non-ideality of the current source, but it's often in practice also limited by transistor matching. So if the two input transistors are not perfectly matched, that will also give you a non-zero common mode gain. The overall result of all these effects, both effects, is then usually quoted in decibel. So then the common mode ratio in decibel is 20 times the log to the base of 10 of the ratio that is shown here. So for instance, if you have a differential amplifier with a 40 dB common mode rejection ratio, that means that the differential amplification is a factor higher than the common mode amplification. So now we'll look at an example of a differential amplifier that has actually been used. It's an historical example, but quite interesting. So this was maybe the first analog integrated circuit that was ever made. And it's one of the two integrated circuits that were part of the Apollo guidance computer, AGC. The other one was a logic gate. And the whole computer only needed a handful of these transistors to read out the magnetic memories. So they created small current pulses when they read out these magnetic memories, and these had to be amplified using differential amplifiers. And they could have built these, of course, from discrete components, which existed at the time, but they decided to go for an integrated circuit. And the main reason was not that they needed so many of those, only a handful were actually built into these computers. But the key advantage here is that the matching of the input transistors is much better than it is when you use discrete components. So this shows a photograph of the die uh, where you have the wire bonds connecting to the circuit, and then these structures here are resistors, and these are the transistors. So let's look a bit at the circuit diagram. It looks a bit strange. It's not drawn the way I would draw it these days. So um, on the right-hand side, you have a redrawing of this, which looks a bit more familiar, but you can convince yourself that this is really a one-to-one translation of this. And now if you look at this one, you can clearly identify the parts that we've seen before. We'll go through this now. So the first one here is a differential amplifier. So here we have a transistor with a resistor as a current source. So we fix this voltage here, and then this gives us a voltage drop here, and then this resistor defines how much current flows here. This current is then pulled from this node here. So this is our implementation of the current source. Then we have the two input transistors, the differential pair. They have a emitter degradation degeneration to have better control over the gain. And then we have these two collector resistance. The next step here is this one, which looks like a common emitter, common emitter amplifier, but it's actually used as a logic gate, because the amplification here is large enough that whenever you see a signal, it basically runs immediately into saturation. So this creates not a proportional output, but it runs into saturation, and hence generates a logic level. So it's high. So when it's high, it runs into the supply voltage. When it's low, it runs into goes down and creates basically a zero, or this Vy. And the third component here is the output. It's a so-called open collector output. This basically connects the logic value that you have here to a bus-like structure, and is turned on by an external strobe signal. So you basically select whether you want to read this bit on the bus or not. Okay, so this was a historic example. Now we look at the simulations of of such a differential amplifier, and want to see how we can basically control the gain of such an amplifier, and ultimately we want to develop a very high gain amplifier from this. So this is the circuit, very much like the one we've seen before. So there's a transistor as a current source. This time we don't set the current through a resistor, but we use a current mirror. So we come in with 10 milliamps here, and then mirror it into this current source transistor. So we know that the current here is now 10 milliamps. We have these two NPN transistors that act as inputs, again with the 50 ohm and 1 kilo ohm. So this should define our gain. And indeed, we now operate this with 100 millivolts differential voltage. So we go up 100 millivolts here and down 100 millivolts there at around a working point of 3 volts. So this is shown here, the input. One is the inverting, one is the non-inverting. And then as the output, we look at this node, and indeed we have a gain that is now uh, we have here amplitude of 2 volts roughly. We have an input swing of plus or minus 100 millivolts, so 200 millivolts, and this is compatible with the gain that we expect, which is 1 kilo ohm over 50 ohms, and then we do this twice because we modulate both sides, so we expect a gain of 10 here. And this is exactly what we see. Okay, so the working point now is given by the current that we send down here. So we operate this with 14 volt supply voltage. We have 10 milliamps going down here. So when this shares equally through both branches, uh, we go down. We have 5 milliamps on both sides. So this one goes down 14 volts minus 1 kilo ohm times 5 milliamps. So here we are at 9 volts, and this is exactly what we see here in this simulation. Okay, so the DC current here affects the working point of this amplifier. Uh, if we want more gain, um, we can drop the emitter degeneration resistors, so these 50 ohms. They define the gain in this case. So this one is an amplifier that has a well-controlled gain. It's set by these resistors. If we don't care too much what the gain exactly is, we just want it to be higher, then we can just get rid of these 50 ohms. And then we have a an amplifier that looks like this. So now we expect a much higher gain. Because now we go from RC over RE basically to RC over little RE, so the built-in emitter resistance, which is 1 over GM essentially. So now we do the same simulation, but we do a much smaller input swing because we expect much more gain. So now it's 10 millivolt input swing here. One goes up 10 millivolts, the other one goes down 10 millivolts, and the output now is again roughly 2 volts. So the gain now is about 80. Okay, the working point is unchanged by this. Um, so this node moved up a little bit, but that has no impact on this node, which is given by the currents that flow here. So now we have we went from a gain of 10 to roughly a gain of 80. Is that right? Yes. We have a much higher gain. Now, what can we do to increase the gain even more? We can either make these resistors larger, or we can increase the current, because that will then basically give these transistors more GM, and so, or in other words, it will give us less emitter resistance here. The problem is that if we increase the current here, we've seen that the working point is proportional to this current. And the same if we increase the resistance, that will just push down, it'll push down these points, and then our working point goes too low, and eventually it'll stop working. So we cannot use these tricks to increase the gain here. This is shown here in these graphs. This is for a 1 kilo ohm resistor. If we have different currents here, then we get different values of the voltage drop across this resistor. Then, for instance, if we have this 5 milliamps as we had before, then we get 5 volts voltage drop. This is the situation that we had. If we go to a 4 kilo ohm, we get 4 times higher gain, but our working point now has to go down by 20 volts. So this will only work if we have more than 20 volt supply voltage. So this is not practical. If you want a very high gain here, you cannot simply increase this resistance or the current to make your gain higher. This will then either need a very high supply voltage, or your amplifier simply will not work. So what we really want is a high differential resistance, but we don't want the large voltage drop. As I said here, and so the IV curve of what we want here instead of these resistors would look like this. So it has a high differential resistance. So it's in this case, it would look like a very flat curve, but it doesn't create the large offset that a high resistance would have. So if we had a resistor, a physical resistor with the same slope, it would create an offset that is huge. So out here in hundreds of volts. Now, if you find a device that creates this kind of IV curve, and put it here, then we could make a resistor with a much higher amplification. Sorry, an amplifier with a much higher amplification. And fortunately, we know such a device, and that's of course the transistor. So this is exactly the IV curve of a transistor when this is the collector emitter voltage and this is the collector current. So this is now implemented here. So instead of the two resistors, we put uh, instead of the two resistors, we put transistors here and we bias them properly such that the current here is balanced with the current that we are pulling down here at the end. So we use a current mirror again that gives us 1/2 of I0 in each branch here, and we use the same current I0 here. And now we see at this point the differential resistance at the output of these transistors, but we don't have the large offsets that we would get from actual resistors. So now it's this RCE of these transistors that determines our amplification, and indeed in this simulation we see a gain of greater than 500. So if you simulate it again with 10 millivolts, then the output immediately saturates. The offset now is around 8 volts and depends on how these transistors scale with respect to each other. Note that these are of course PFETs and these are NFETs, so they are not the same transistors. So the current mirror here has to be made from PFETs. So in order to get the working point right, you need to fine tune these currents a little bit. So this is kind of difficult, and there is in fact a much nicer solution, and that is shown here. So instead of biasing these current sources with an independent current source, we configure them as a current mirror with PFETs again. So this one here now takes the current on this side and mirrors it, tries to mirror it over to the other side. Now this gives us actually even additional modulation, because we not only have the modulation through the fact that these transistors share the same current, but they also now share the same current here in some sense because it's mirrored over. So this gives us a factor 2 in the gain of this amplifier again. But again, the working point is very sensitive. And such a high gain amplifier is very difficult to use. So there are the very few applications where we really come in with a small signal of a millivolt or a microvolt and want to directly produce a highly amplified output. These are usually used with so-called negative feedback, which we'll come to later. So this type of input stage or differential stage is very often used. It gives you a nice high gain, but it's not perfect. So there's a certain asymmetry between the inverting and the non-inverting. First of all, because we have the current source, the diode connected transistor here, and we don't have the diode connected here. Instead, we have the output. So this one swings up and down, while this one is almost constant. So this means that on the inverting input, which is this one, we have a Miller effect. On this one, we don't. The other disadvantage is that the common mode of these two transistors basically limits the output swing. So when both of these transistors move up, then the output cannot go below this input. So we're slightly restricted in where we can go with output and input with this. And these disadvantages basically come from the fact that the output node here is now part of the same current branch where the input node is. And now we'll develop a circuit that is a bit more complicated, which avoids this. Although this is in fact something that is used very often, but I will now show you something that avoids this problem. As we said, this circuit has some small disadvantages because the output is now here as part of the input branch. Now we cut this open, and instead of mirroring it directly, we mirror the output branch or the second input branch to another one. So now this current here, oops, this is wrong. This should be, so this diode clamp is only on one side, not on both sides. So this should be gone, sorry. So this current here is mirrored over into this branch. So, sorry, there's a mistake. These are of course not diode connected, only the central parts. Sorry. But so the idea is now that we mirror this current over to the other side, and then we mirror it again and bring it back here with the second current mirror to the input branch. So now we have the effect that we had initially with the current mirror between them, but we avoided the fact that the output is directly inside this branch. Now the output node is here, and it will go up and down when we have a difference in these two voltages. Now the gain of this output is given by the early effect basically in this transistor. So if you think of this small signal model here, now then you have the current sources here with these parallel resistors. So when you're at the working point, these are exactly balanced, so they both have the same current. So this one sends a current down and this one absorbs the same current. But if you now change the current balancing here, the output node will go up and down as a function of these collector resistances. So in the small signal voltage, you can now calculate the gain of this thing, and it's given by the parallel of these two collector resistances multiplied by the GM of the input transistors, and then still the same as the thing is proportional to the difference of the input. So this gives you a very high gain because you multiply the GM with the output conductance of these two resistors, the transistors. So the big advantages of this are now that the input can really go up and down rail to rail, so it can go from 0 all the way up to the point where you shut down this current mirror. So there's basically no restriction for the inputs, and the same is true for the outputs. Also, the output can go from rail to rail without any restrictions. So these are some very ideal properties of a differential amplifier. So it is, however, quite sensitive to any current loads at the output. So if you connect something here like a capacitance or something that or a resistor that draws a lot of current, it will affect the current balance here. So these are not extremely strong transistors typically. So whatever you connect here affects the gain of this transistor. So typically of this amplifier. So typically what one does is that such an input stage is accompanied by a second stage that buffers the output. But this is not the only possible design for an input stage, and we'll on the next slide see actually a different one. This is just one that is frequently used, and this is a modification of it that makes it quite ideal. So this picture is a slide that I took from Ron Torresberger, who gave this lecture a few years ago. It shows is a summary slide of a classic operational amplifier. The diagram is shown here. It may be a little bit confusing and it's not so easy to understand, but if you look at it for a while, you will recognize a couple of things that you've seen in this lecture. So the input stage is shown here. It's a different kind of input stage, but it's not too different actually. So what we have here are the two input and resistors, transistors, the non-inverting and the inverting, but they don't modulate the currents directly. They are basically operating as followers here. So they reduce, so they increase the input impedance. So they run as followers here, and then define the emitter potential for these two. And these are the actual modulating transistors, but they're not connected in the way that we've seen on the previous pages here. They're used in a common base configuration. So the base is sort of fixed, and the inputs modulate the base emitter voltage of these transistors. Okay. So this is a slightly different use of the transistor, and this modulates then the currents that flow down in these two branches, but the rest is pretty similar. Here's a current mirror, which completes the differential pair. So it's upside down with respect to what we had before. We have the current mirror here. The feedback of the current mirror, the emitter, the diode connection is also slightly different. It's not simply done connecting these two parts, but there's a transistor here between, or an emitter follower if you want. But basically, this is also just a current mirror, and this is our differential pair. Uh, f- uh, for a real world amplifier, it's important that you can make sure that the offsets are small, and this one actually has the way of modifying these offsets with external pins. Um, so this we never used, of course, in our idealized amplifiers, but when you have a real system where it's important to compensate these offsets, then these operational amplifiers sometimes have these inputs that can help you with external resistors to modify these current mirrors to make sure that the offset goes away. Um, Other parts here are maybe also known. This is the output stage. These two transistors operate in a push-pull configuration. Um, and there's another gain stage in between, which takes the input of the differential stage. And then this part here is like a common emitter common emitter amplifier. It's a little bit complicated. So these two transistors are coupled together. They form a so-called Darlington pair. Uh, so um, so the output of this transistor, the current from this transistor is fed directly into the next one, making these two look like one transistor which has a super high beta. So the beta of these two is basically multiplied, because you take the base current that flows in here is multiplied once, and then it flows in here and it's multiplied again. So this is a so-called Darlington configuration, but they look like one huge beta transistor, and this is the collector load for this transistor. So this is a very high gain stage as a second stage. So here we have three stages actually. So there's the input stage, there's a second gain stage, and there's an output buffer in a push-pull configuration. Maybe some other things you may recognize are lots of current mirrors here. This is a current mirror. This is a current mirror, slightly modified again. We have a emitter degradation here, a degeneration here, which attempts to modify the current. So this is the main biasing circuit, by the way. So this resistor here operates now between these two transistors. So this one is the positive rail, which is plus 12 volt typically for this one, and this is the negative rail, minus 12 volt. This is in a diode configuration. So here you have the minus 12 plus zero point 0.7 volts, and here you have the plus 12 minus 0.7 volts. So the voltage across this resistor is constant, and this creates a constant current here. And this current is then mirrored to several places and used to bias these circuits. So you don't need to understand all of this. We'll look at a simpler operational amplifier in the next couple of slides. Just some numbers. This one has an amplification of about 200,000 with all the three stages. Today you can also buy operational amplifiers which have much higher gains, but this one is still available. It has a very high input resistance in the mega ohm range, and the input offset is another important quantity, is small and can be compensated. This one tells you the point at which the gain drops to 1. We'll come to that in one of the next pages. It can be bought in different packages. You can buy them in these packages or in a dual inline package, and we'll use something similar in the practical exercises. Okay, let's move on from this real world op-amp to a toy op-amp, which is a little easier to understand. So now we have a differential input amplifier, the classic style with the differential pair, current mirror, and some current source biasing. Then we add an additional gain stage here. This is a common emitter transistor, common emitter amplifier, and with these two resistors defining the gain, so the 50 over 1K. And here we have our push-pull output buffer. In order to make in order to avoid the crossover distortion, we added these two diodes here to make sure that this one that one of them is always on. So this is, maybe you remember this from the push-pull stage. So this is a very simple but in principle functional operational amplifier. Note that there's no AC coupling anywhere, which is important for an important criterion for uh, operational amplifiers, so people can use them down to DC. And in the practical exercises, we also used an amplifier that had a AC coupling at the input. This works fine, but only for high frequencies. So there's a lower cutoff where it doesn't work. But these operational amplifiers are often used at DC, so there can only be DC connections inside such an amplifier. Okay, so let's simulate it here. So this is done with discrete transistor simulation. So we have the 2N2907 and the 2N222 for the NPN and the PFETs. We used 15 volt supply voltage, and we come in with 0.1 millivolt input. And then we see already some amplification at the output of the differential stage, which is shown here. So there's an amplification of about 1000 from the 0.1 millivolt. We go to 200 millivolts here. So there's already an amplification of 2000. And this is amplified again now. And the total output swing is shown here, where we see now basically a total gain of 20,000. Okay, so this is already quite a usable amplification. But as I said, these amplifiers are normally not used to amplify such small signals. Most of the time, they're used with feedback, and this is shown here. So we now make a feedback connection from the output to the inverting input, and we only use the non-inverting input. And this is called a buffer configuration. So what happens here is now the output voltage is given by amplification times V plus minus the output voltage. So if you rearrange this, then you have the output voltage divided the output voltage times A plus 1 on the left-hand side, and A plus V plus plus the offset here. So in the end, the output becomes A over A plus 1 times the voltage here, and then 1 over A plus 1 times the offset. So this is roughly the same as V plus. If you now think that A is a number like 20,000 or even higher in many cases, this factor becomes 1 and this one becomes negligible. So our output will become a copy of the input. So this is we call this the gain of this buffer is 1 for an open loop gain of the amplifier, which is much larger than 1. The other feature of this is that the feedback also makes the offset of our amplifier irrelevant. Okay, let's see what happens when we do this not in DC, but look at the transient. So we have a voltage change here that goes, no, it goes from 2 to 3 volts, not from. So here you see a voltage step at the input that goes from 2 to 3 volts at 10 seconds with 1 microsecond rise time. And we expect the output to do the same. But unfortunately, what happens when you simulate this, or the same would happen if you build it, this is not what you get, but instead, the amplifier oscillates all the time with a very high frequency. And this is called instability. And the question is, why does that happen? So you've seen that this amplifier has several stages. Now consider a system of 3 stages, each one with some amplification. The overall DC gain, now with the open loop gain, is the product of the 3 gains. And as long as the overall gain of this is a negative number, this will be stable. Then we have so-called negative feedback. Then whenever you go away from your fixed point, the amplifier will drive it back to where you come from. However, if the overall gain of this is positive, then you start up getting positive feedback, and whatever deviation you have between this output and where it should be, it drives the input to make the amplifier go away from the stable place even further. So this will go. This is an unstable configuration if the gain is positive. Um, Now we can use this amplifier model that we have with the three stages, and any realistic amplifier has internal time constants. So we model these with these RCs, and then we get to this picture. And now the complex gain for for a given frequency is given by this. The A123s are the DC gains, and they are modified by these factors here for the RC, which have different time constants. And the overall thing is then the product of these two multiplied by a phase. And whenever this phase becomes 180 degrees, our amplifier will be unstable. So in DC, of course, it's stable, but this thing are complex and can eventually become 180 degrees, and then we have an unstable amplifier. This is shown here in a Bode plot. This shows the amplification for the situation where we have three different time constants here, 10 to the 3, 10 to the 5, and 10 to the 6 hertz for the three stages. And what you see here is that the gain is constant for a very low frequency. Then the first pole kicks in, and you see a drop of the gain. And when the second pole kicks in, you see a steeper decrease of the gain. And at some point, the overall gain will reach 1. Now, what also happens is that the overall phase of these three RC stages starts to change. So the first one, it goes from 0 to 90 degrees. From 0 to 90 degrees. And then you come to the next one, and as you go through it, it starts to turn to 180 degrees. And if you reach the 180 degrees, while the gain is still larger than 1, the amplifier will start to oscillate. So in this particular case, your amplifier will oscillate roughly at 0.3 megahertz. So the cure here is to move the lowest pole to a much lower frequency to make sure that the point where the phase reaches 180 degrees, that at that point your gain has dropped below 1. Okay. So if you're just there, if you just make it there, so we're running out of time here. I'll just show you that this actually works. So this is the situation that we had before. So the amplifier oscillates. Now we add this resistor here, and this moves the first pole to a very low frequency, and the whole circuit with feedback becomes stable. This is called compensation. Um, and most op-amps that you buy these days are internally compensated. Often these large resistors, these large capacitors that you need are implemented using the Miller effect, for instance, in the one that we just saw. Um, but not all of them are. So you have to look into the data sheet. Some op-amps are not internally compensated, and then you have to be careful how to use them. But those that are compensated are very safe to be used in feedback, but they are typically slow. So when you need something that is very fast, you may want to look for one that doesn't have the internal compensation, but then you must be very careful and expect problems with oscillations. Okay, that's it for today.